Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Hui Deng, who is Professor of Physics at the University of Michigan. Her research centers on the discovery, creation, control, and applications of quantum states in single, few, and many-body systems with matter-light couplings. Welcome, Hui.
Thank you, Gil.
So I want to start with, you have a few papers, recent papers. I want to start with one of them, van der Waals heterostructure polaritons with moiré-induced nonlinearity, in which you say controlling matter-light interactions with cavities is of fundamental importance in modern science and technology. This is exemplified in the strong coupling regime where matter-light hybrid modes form with properties that are controllable by optical wavelength photons. When you say matter-light hybrid modes, that is a new phenomenon, is it?
Yes, that's a very interesting phenomenon indeed.
So can you give some context around how that happens? And I know that you have some experiments at Michigan. So could you set the context for maybe go back a few years? When did we first discover this phenomenon?
So these hybrid modes, which we call polaritons, this traces back to a century, even many decades.
Okay.
It itself is actually quite a general thing.
Yeah.
Right. So it can be in all kinds of different systems. So in general, when you have electromagnetic waves that couple very strongly to matter excitation or excitations in matter, typically involving some form of electronic motion, then you can form polaritons. Okay. So polariton itself is actually a very general phenomenon. It exists in metal, in solids, in insulator, in semiconductor, in atomic gases as well, in all kinds of forms.
Okay. But when you say hybrid modes, so what exactly is a polariton? Is it a photon? Right. Is it a photon or is it something different?
It's a hybrid. So the condition to form polariton is the strong coupling is strong enough. The coupling is strong enough, and what that means is that it has to be a type of excitation that can couple to the electromagnetic field. Yeah. For example, the electromagnetic field, or let's just say light, can excite this excitation in the matter system. It could be oscillating electrons, and in our case, in semiconductors, it is a electron and a hole pair in the semiconductor, which we call excitons. Then the exciton, so in quantum mechanics, everything is reversible at the microscopic level.
Yes.
So light can be absorbed by the matter to create excitation. Then the excitation can return the energy back into the fields, or to send it back into as a photon or as light. And so typically the interaction is not strong enough. So this process that you absorb a photon or absorb light and then re-emit light can be considered as two distinct processes. There is a decoherence, etc., that happens in between, and the light that comes out later does not have memory of the light that came in earlier. So that's the weak coupling regime that most of the time we deal with in our daily life on systems that interact with light.
Yeah.
So in the laboratory, we can get to what we call the strong coupling regime. That is when, in the way you can think of this absorption and re-emission process becomes very fast when the coupling between the excitation and the light becomes very strong, and it becomes faster or stronger compared to other decay or decoherence processes, or processes that destroy the memory or destroy the what we call quantum coherence. And when you go to that limit, then when you send some energy into your system, you don't really know if you have it in the form of light or in the form of this electronic oscillation. And in fact, what it is indeed it exists as in both, and that's why we call it a hybrid, matter and light hybrid.
Yeah. If I understand it at a very high level, so light interacting with some sort of a matter substrate, maybe a semiconductor or something like that, and light is exciting matter in that substrate, and that excitation can have a lot of different features. And so if I understand this correctly, Hui, correct me if I'm wrong, some sort of synchronization, light goes in, excites the matter substrate, and that excitation then in turn can produce light. And so you can sort of go back and forth between those two things, right?
Exactly.
And so there are a lot of quantum related interesting things that happen. When one of them is, if I understand it correctly, one of them is this entanglement, and so that the photon that is going in essentially gets entangled with that matter substrate.
That's a very good question. It can be sort of as a form of entanglement.
Yeah.
It sort of depends on what you want to use the entanglement for.
Yeah.
And for example, if one is interested in using entanglement for quantum information, then we need to ask a question how we can verify the entanglement and put it into a form into certain quantum algorithms or protocols. And in general, it's an extremely difficult problem if you have a many-body entanglement. Even how to quantify this form of entanglement is still in general, open question.
Yeah, so you mentioned sort of the light memory. So a photon going in and creating an excitation in the matter substrate that subsequently leaves a photon back, and those two photons going in and coming out have some sort of memory.
They don't. So the memory may not be very rigorous way of describing it.
Yeah.
So the memory I think I referred to was within this polariton system.
Okay.
So once the energy is sent into the system, it could, if we make a classical analog, we could think of an energy. We can think of the energy goes in between the matter excitation and the photon, and back and forth. And in this process, they sort of keep the phase information or the correlation, phase correlation at different time, the different positions. And in that sense, it has the memory of the between the matter system and the photon field. And when this energy eventually comes out of the system again, if it is through a spontaneous process or spontaneous emission, and that photon comes out as a different photon or different light than the one that initially came in. But within the polariton system, this strong coupling leads to this coherent coexistence of the matter excitation and the light.
Yes.
So I guess we can also make an analogy to uncoupled harmonic oscillators in a way that is really a mathematical model for the system. If we have a spring with a mass attached to it, it will oscillate at a certain characteristic frequency. The jargon is eigenfrequency. So you can have another harmonic spring and will oscillate also at its eigenfrequency or its characteristic frequency. And they are two separate oscillators. Now you can add another spring to connect these two. And that's basically providing coupling between these two initial uncoupled springs. Then when that spring is sufficiently strong, then when you try to make one of the oscillators, the springs to oscillate, it will affect the other one. And it can no longer oscillate at its original eigenfrequency. Instead, the two will oscillate together with a new characteristic frequency. And you can think of these two oscillators. One is our matter excitation, one is our light. Now the coupling is strong enough, they start to oscillate together and in the new form with a new frequency.
So this phase correlations that you talked about. So clearly computing with light is a lot more elegant, a lot faster. So will this move into, we will have some effects on quantum computing and other type of things?
Right. So coherence is very essential to quantum computing or quantum information science. And the grand challenge is how to harness it and control it. So there are a lot of effort and ideas of using polaritonic system to do that. And the reason or the rationale is it is a metal-light hybrid system. So it has the advantage of both. It has the advantage of a light system, which is the pure light doesn't interact and have extremely good coherence properties. So it still inherits some of that, even in the hybrid form. While pure matter give you interactions because they do interact, and that's what you need for information processing. So when used in the right way, you may be able to combine the advantage of light and matter with the hybrid system.
Yeah, and if a quantum system, so since it's a macroscopic system, it might also allow us to test some of the quantum questions on this. In other words, we don't see quantum effects in macroscopic systems typically, right? So this one, it is sort of, it's a macroscopic system, isn't it? You have matter involved. So just take me back to the experiment that you ran. So how exactly would you produce this in the lab?
So we typically use a piece of semiconductor as our matter system. well, very much look like a chip, like the tiny chips in our phone or in our computer. Then we would mount it somehow. And okay, to create the polariton system, we basically have to make the interaction between the electronic excitation and the light to be strong enough. And to do that, we take a typical semiconductor, but put it inside a cavity, and which is basically what strongly confines the light field and amplifies the local field intensity at the position where we put our matter excitation. And that's sort of how we construct the system.
Yeah, and so what's the scale we are talking about? For that cavity and the matter involved in the system, what is sort of the scale?
Right. So the device can be, in principle, any size. If we're talking about the size of the quasi-particles, like if we compared to, for example, size of an electron or atom in that sense, that typically refers to the size of the quantum mechanical wave function. And so for polariton, the wave function depends on the potential confinement. So for electron in vacuum, for example, it actually has the infinite size if there's nothing else to interact with, because it should have a plane wave function, which means it extends the whole space. So there is another size which is in the sense we can call it a coherence length. Means if you take the wave function at one point and take it at a different point to see whether or not they're always phase correlated. For example, you can do interference or Young's double slit experiment. That coherence length of that wave function would be very short for matter system, but for the polaritons, that is largely determined by the coherence length of the light part, and that's typically on the micron scale. Then it depends on how good a cavity we can make. So it is typically a few microns to even up to hundreds of microns.
So I don't know a lot about this, Hui, so I'm just asking this question. So going back to the double slit experiment, and the waveform collapse, the Copenhagen interpretation, are there things that we could test with this system?
So I think a lot of things have already been tested. The quantum mechanics is very mature. So if we go back 100 years, and then there are many open questions in quantum mechanics in terms of how to interpret, if you could see matter wave interference, and which was done with electrons. That's called one of the most beautiful experiments in physics. And the polariton system certainly, if people knew how to make it and how to study it, would have made such experiments much easier to do. But then a large number of those foundational experiments have already been performed to understand and verify quantum mechanics. And I would think the real advantage of the polariton system is for to actually make use of this quantum phenomena rather than testing the unknown realms of quantum mechanics itself. And that is probably best suited by precision measurements.
Okay. So in another paper, you talk about the Polariton Laser. So this is a microcavity exciton polariton that you talked about. So microcavity exciton polariton systems can have a wide range of macroscopic quantum effects, you say, that may be turned into better photonic technologies. And one of them is a laser?
Right.
So what is special about this laser?
Right. So laser is, of course, almost ubiquitous. So it's one of the most important technologies nowadays. And it is used more and more in information technology. So there is a lot of interest to reduce the power consumption of those lasers and create nano lasers, micro lasers. And so what's special about the Polariton laser is that it gives a laser-like emission through a very different mechanism compared to conventional lasers that would enable it to give out such emission at a required minimum energy input that is much, much lower than required for conventional lasers.
So required energy much lower. So does that also imply that you can create more powerful lasers?
That's a great question. So it does not imply more powerful lasers directly, and it reduces the minimum energy input. So you could perform tasks that require coherent light at a much lower at a much lower energy input. And to get more powerful lasers, then we have to see how well the system can scale up. And there are ways Polariton may help because it has a stronger nonlinearity compared to normal semiconductor lasers, and also have more control over their property because of this strongly hybrid nature of the quasi-particles. But how to implement that will depend on the system details.
Yeah, for a the hybrid nature is really perplexing. So this hybrid thing, photon matter thing, it should have some very interesting properties, right? I mean, how do you explain that?
You mean how to understand how this?
How do you understand? So when you say hybrid, you mean sort of the exciton and photon thing together, right?
Right.
Okay, and so it's not an entity by itself. It's really a process by which a photon is interacting with the matter substrate.
In a way, you could think of it as a quantity itself. So in physics, we talk a lot about quasi particles, not real particles, like the electron in the solid. They are not real electrons anymore. We still call them electron, but they have a different effective mass, for example, compared to a real electron in vacuum. And even in metal, where the electron can be considered almost, we call it a free electron gas, and has the electron charge and moves with the electric field, etc. But they still feel what is happening in the lattice, the underlying lattice, and that gives them a different mass compared to an electron in vacuum. So even the simple electron in the metal is already a quasi-particle in the solid state, in the solid. So the polariton is just another kind of a quasi-particle. It is considered as a particle in the sense that you could measure its effective mass. You could measure its charge, which is 0. You can model it as a particle in your equations, in your Hamiltonian, and with a mass, with the interactions, and with a certain lifetime, how long it lives before it leaks out, etc. So we call those eigenmodes of the system. That's why they are good quasi-particles of the system. So it is becoming an entity of itself.
Yes, it's as you say, a quasi-particle with some fundamental properties you can measure, like charge equal to 0, small mass. Will it have some limit on speed? It cannot have a speed of velocity of light, right?
Right. So yes. So there is the speed you're referring to are probably the group velocity, basically how fast the information can actually move or get transferred, and that can never go faster than speed of light. Otherwise, we may violate causality, and that is true. Only light in vacuum or zero mass particles in vacuum can go at the speed of light. And this polariton certainly cannot go at the speed of light. You take the effect mass, or more precisely, you take how the kinetic energy changes with the momentum, and take the derivative that gives the group velocity.
And just very approximately, how much less would the sort of the speed limit on the polariton?
In principle, you could sort of control the optical mode to make a polariton that go very close to the speed of light. In common types of systems, we typically have the group velocity of maybe about 10% of the speed of light.
Yeah, because if it is potentially have some practical applications in computing, then the speed becomes important. And I think the low energy lasers you talked about, would they have a direct application in computing as well?
Yes. So the laser actually have been used a lot in computing already. There are very active research on optical computing architectures that will also rely on laser a lot. So the laser would be used to generate the signal, and one can also modulate the laser as a way to modulate the signal. And then optical interconnects would also benefit using coherent light.
Yeah. And purely from a practical perspective, you observe this phenomenon in very low temperatures, right?
And that's right. In the papers I sent you, we observe it at low temperatures, because we want to sort of have the clean the system and understand the physics from the most essential part first before we add the complications.
Yeah.
So a lot of the work on such as the polaritons and the polariton lasers were initially done in materials that polaritons can only survive at very low temperatures. And the exciting thing about more recent development in material science is there are materials that do support very strong exciton and excitation, the light interaction, to give very robust polariton modes, even at high temperatures, room temperature, or even higher. And certainly it's a hope that we can eventually be able to do all the interesting things with the polaritons at the room temperature.
Yeah, like superconductivity. You observe the phenomenon at low temperature, but over time you can move that up to. But you're saying there are materials already at room temperature that could potentially be used here.
Yes. And in the paper, the van der Waals material polaritons, the van der Waals materials is the type of material that support polaritons at room temperature or higher. Then the challenge is improve their quality and figure out how to control the phonon baths, interactions of the phonon baths with the polariton systems. And then gradually you will be able to keep the coherent phenomena we want to make use of to survive at higher temperatures.
Right. I want to go into another paper you have, Emergence of Microfrequency Combination via limit cycles and dissipatively coupled condensates. You say self-sustained oscillations, limit cycles are a fundamental phenomenon unique to nonlinear dynamic systems of high-dimensional phase space. They enable understanding of a wide range of cyclic processes in natural, social, and engineering systems. Could you talk a bit about that? I'm intrigued by natural, social, and engineering systems.
Right. So the limit cycle is a phenomenon in nonlinear dynamic systems. And so it is a very basic phenomenon in nonlinear dynamic systems, and that's why underlies a very broad range of phenomena. In natural systems, some of the first examples people begin to study in this context is like predator and prey cycle, and there is a certain feedback, and it's not a linear feedback, and that leads to this type of a cycle. There's no initially there's no obvious parameter that's already there to set, for example, the period of such a cycle, or where the equilibrium is reached at, and that is established simultaneously through this nonlinear dynamical process. So in engineering systems, for example, we sometimes hear whirring of wires, and that is one of the classical phenomenon coming out from the limit cycle, which is suddenly it starts to vibrate as a certain frequency that was not otherwise not its eigenfrequency otherwise, but it comes out through the nonlinear dynamic interactions.
Yeah. And what's the social system that you're talking about?
The social system, I think, some example included spread of the disease, actually. Really, like in the pandemic, how the disease started to spread, and how widely it is spreads, and what's the time frame of the spread and the cure, this type of cycle.
And so the mathematics you're saying underlying this is prevalent. It's prevalent in different systems, right? And so how does it connect with polariton cavities?
Right. So in the polariton cavities, we basically have nonlinearities in the polaritons. That's why we can model it as a nonlinear dynamic system. And given a nonlinear dynamic system, whether or not the limit cycle is a solution is also an extremely difficult question in mathematics. It does not have a general answer yet. It's one of the million-dollar questions that's being posted. We know the solution exists for certain types of nonlinear dynamic systems, but we don't have a general answer. So, and those are also, nonlinear dynamic systems are also in general very sensitive to the conditions, initial condition and the system parameters. And so generally speaking, it is quite difficult to create and control such a system in slightly more complex settings. They very commonly appear and underlie a wide range of phenomena. But if you want to artificially create and control one, actually can be quite challenging. And to understand the phenomenon quantitatively and understand whether or not it results from that is also challenging. So it just happened that we found that this polariton Polariton system with a nonlinearity and with its dissipation built in. And in the coupled polariton cavities, basically two polariton cavities coupled together, there is actually simple set of equations, and you can solve it. And it's turns out there is a very rich phase diagram, including a part of the phase diagram where you can satisfy the condition for the limit cycle.
Yeah, it's fascinating. I don't know if you see it this way, but engineering is advancing so fast that you're able to actually experimentally show things that are not really sort of theoretically and mathematically laid down on paper. Do you think that is sort of what's happening in high energy physics today?
Yeah, high energy physics is a little. I'm not sure. I think it might actually be the other way around. Theory is much more ahead of experiment in high energy physics.
Yeah. But this one, since you are seeking sort of a solution, a mathematical solution for this, it seems like if you find that you have predictability, you have a better quantitative understanding of the system, but you already sort of demonstrated that it is working.
Right. So that's an excellent question, and the nature of the research in of solid state systems is sort of like that. You have a theory that predicts things, but the theory is always a model because solids are complicated, right? Even a tiny piece of solids have 10 to 30 atoms, 10 to 23 atoms, and so on. So you can't track them perfectly. You can't have a complete ab initio equation and solve it to find out what is going on. So it's always a modeling. And until you see it in experiment, you never know if your model captured the most important factors or missed some of the essential physics. So the theory will predict a lot of things, and that give a lot of guide to the experiment, what to look for, and what may be something interesting that could happen when we do this and that. Then at the same time, you try that, you do it in experiments, and you will see a set of phenomena. Some of them may be predicted by theory, and some of them may catch you by surprise. And that's sort of what happened in the lab when we saw those microfrequency combs or these additional frequencies appearing. We did not really expect it. We did not know what they are, but it just happened in this particular case. When we looked back into the literature, we find a theory and realized, oh, that is what is happening.
Yeah, and it is it's such a fascinating area because it's sort of quantum effects in macro systems, and because there's a lot that could be learned through this behavior. It not only has practical applications but also potentially improvements to our understanding of quantum mechanics.
We certainly hope we can make some progress on those fronts.
Yeah. And so in conclusion, Hui, so I know that you're doing a lot of work in this area. So if you look forward 5 years, 10 years, from a practical perspective, where do you think this type of technology could move into?
I think it could move into novel photonic devices that can have either has a performance that cannot be reached by existing known architectures of photonic devices, or even could have functions that's not realized in today's devices.
Yeah. So, and these devices are largely in the area of computing, or other devices as well.
As well as in possibly imaging and sensing.
Oh. Okay. Excellent. Yeah, this has been great, Hui. Thanks so much for spending time with me.
Thank you.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.